We've been dealing with simple higher order differential equations like with constant coefficients, and so now what we want to do is we want to extend beyond that. Although to make it as general as possible might be kind of difficult, so we're going to take a look at a special type of differential equations called the Cauchy-Euler differential equation. And if you look at it carefully, you can see that there are non-constant coefficients, but those non-constant coefficients have a special pattern. They have to actually match the y derivative with the power. So Cauchy-Euler equation is going to be equation of this form where you have some constant times n or x to the nth power, and then that x to the nth is being multiplied by the nth derivative of y, and then a bunch of linear combinations of the same pattern. And just like before, what we're going to do is we're going to consider the homogeneous way of solving for this first, and then we'll use the variation of parameters to help us figure out a particular solution. Okay. Now, when we first did the higher order linear differential equations with constant coefficients, we said let's let our solution be equal to y is equal to e to the m times x. For the Cauchy-Euler equations, what we're going to do is we're going to assume our solution is going to be a little bit different. We're going to assume that our solution is x to the m power. And then we're going to plug it in, and then we're going to see if we can get the solutions from there. Okay, so that's our plan. Okay, let's do an example. So I unlocked the door on the outside, so you walk in. Is that clear? Everybody? Just going. All right. So first, we could take a look at this example over here and realize that it is, in fact, a Cauchy-Euler equation. We have, it's a second order differential equation. We have x to the second power times y double prime, x to the first power times y prime, and then we just have a constant times y. So this is, in fact, a Cauchy-Euler equation. So what we're going to do is we're going to assume that our solution looks like x to the mth power. And then we'll take a couple of derivatives and plug it back in to see what we can get, and hopefully we can solve for m. And so if we take two derivatives, y prime is equal to mx to the mth minus 1, and y double prime is equal to m minus 1 x to the m minus 2 power, then we can plug those in and see what we get. And the nice thing about this is that you'll see that after you plug it in, you'll have x to the nth power all matching up in each of those terms that you can factor. So we have x squared, then we have m minus 1 x to the m minus 2 power, plus x times x m minus 1 plus 4 times x to the mth power is equal to 0. And then you can see that if you combine the x's, I'm going to get x to the mth power for each of these terms. m minus 1, x to the nth power. And you should look at that, understand it, feel comfortable with it, because we're going to do this with series a lot, matching the x powers and stuff like that. So if we factor out an x to the m, we could set that equal to 0, but if we set that equal to 0, that's just x is equal to 0, which is not something that we really care about. So we're going to see that we're going to have what we're going to call a characteristic equation again. And we're trying to solve for m here. So we can set that equal to 0. Okay? Any questions so far? Yeah, so these two get multiplied to equal, so we're adding the power. So m minus 2 plus 2 is just going to be m. And the same thing is going to happen with that. Okay? All right, let's see if we can solve for this equation now. We have m squared minus m plus 4 equals 0. We got m squared plus 4 equals 0. So m is equal to plus and minus 2i. So I got complex numbers. Probably not a good example to start with, but so how are we going to deal with this? So our solutions are supposed to look like this. So unfortunately, we this is a complex function. Complex is in imaginary numbers, complex numbers. This is a complex function that we can't really, we start off our differential equation was a real number differential equation, so our results should be real numbers. And so what was that formula when we had a complex number thing happen? E to the what? Well, it's something to do with the series. Yeah, sine and cosine, right? And so the series kind of helped prove that the sine and cosine, but what is the actual formula? Well, that's the result. What's Euler's formula? E to the beta, or e to the I theta. So the complex number is in the I. It's what? So if we remember, we have a formula for dealing with complex numbers if it had an e in it. So e to the I beta is equal to cosine beta plus I sine beta. And then from there, we kind of picked out our functions and just looked at sine and cosine. Yes, the I is just with a sign. cosine is the real part. So, but we don't have an e, we have an x to the power. Can we force an e in there? Right, everything to the e? Well, if we can, that would be cool. But if we take it to the power of e, then, or if we take it as a power of e, then it different function. Make x equal e. No, close. There's a rule to try to get this with a base e. Log it to the base x. Sure. E to the ln of x to the 2i. Isn't that the same thing? So I have x to the 2i, and I want something equivalent to x to the 2i that has an e in it. But if I just take it as e to the x to the 2i, that doesn't make sense. That doesn't work. But if I write it as e to the ln of x to the 2i, that's exactly one of my solutions, or how my solution is supposed to be, right? So I'm kind of almost there, except this has to be e to the I beta, right? So there's another rule for exponents, or for logarithms. Yeah. The 2i, e to the 2i, and then ln x. So there's an I in there now, and then there's just the 2 ln x. So now we can write it using Euler's formula. So this, according to Euler's formula, is cosine of 2 ln x plus I sine of 2 ln x. Now we could go through the same argument to say, okay, we could do that for this one, and we could do it for the negative 2i. We could do it for the negative 2i, and then we'll get another cosine 2 ln x, this time with a minus I sine 2 ln x, and then linear combinations and stuff like that. We want two linearly independent solutions. So the two linearly independent solutions would just come out of this. So I think we have our answer. So your y1 would be the one with a cosine, and then your y2 would be the one with a sine. And that would be our solution. Well, we write our solution in with the extra constants.
What if it has like a plus, you actually looks like
Oh, then you would work that out in here too, and then you'll have an extra e to the something on the outside. So again, this is probably a deeper example than we should have done, but this is the one I accidentally picked out. So, okay. So the general idea is to come out with this equation, and then solve for that, and then find your solutions and write it as x to that power. And then from there, you get your choices. Yeah. Yeah, so I is it's a complex number, but it's really just a constant. And so that can kind of merge in with the C, but we don't look at I as complex numbers. Kind of like what we did before with when we had this, we used this Euler's formula before, and the I just kind of went away. We ignored it. We kind of just used it to help us solve for the equation. I like to think about it as going into the complex world and then getting your solution and then coming back to the real world and say, we don't need those I's anymore. Did I tell you we're going to go to different worlds later? Yeah. All right. So in general, we have a summary of results. For the complex, or for not for the complex, for the Cauchy-Euler equations. So I'll just put the summary results and then we'll take a look at some examples. Why is it blue? Can you guys see? So we're going to come up with that equation. Actually, let me add on our general equation here. Get ax squared y double prime plus bx y prime plus c y is equal to 0. We're looking at the homogeneous portions of it first. And then we're going to let y equal x to the mth power. And then we're going to get a x squared. The derivative, the two derivatives of this is m minus 1, x to the m minus 2. So that's y double prime. For b, x, the first derivative of this is m x to the m minus 1 plus c, and then it's just the original function. And so we can combine the x's again, and then we all have a factor of x to the m power. And then what we have left is an m minus 1 times a plus b times m plus c is equal to 0. So this turns out to be your characteristic polynomial. So it's different from the other ones that we've done where the first order is just ax squared plus or am squared plus bm plus c. Here it's a little bit different because when you take derivatives of x to the m, you get some extra constants coming out. So it's a slightly different characteristic equation. So you could do one of two things. You can memorize this characteristic equation, or you can just go through the process, which takes another extra minute or two, but it's not too bad. So if you're good at memorizing, just go ahead and memorize what's in the box. If not, just go through the process. It's not that bad. So given your characteristic equation, you can have two distinct real roots, in which case it's just x to the mth power, and then those two different m's will be your powers, and then that's it, you're done. And the case 3 is the example that we did, where it becomes a sine and cosine of beta times ln x. Somebody asked, Luis asked, I think, what if it's alpha plus I times beta? Then you get this extra x to the alpha business that would come out. I think the more difficult case is this thing where if it's a repeated root, then instead of multiplying by x, you're actually going to multiply by ln x. And you can prove this by doing the reduction of order formula. So I'm not going to do that. You can if you want. Sounds like a good test question. I don't know. So that's how they would have gotten the second solution, by reduction of order. Okay. So let's do some problems, some more problems. And then after we do a couple more problems that are homogeneous, we'll do maybe one or two that are non-homogeneous, and then use up that last section that we did where we did variation of parameters. So let's do some examples. Oh, we can go higher order too. Let's just go to the second order right now. Let's 1 through 12, 14. Pick a number from 1 through 14. 9. All right, so let's do this example. We are going to, I'm going to think about, I'm not going to memorize the formula just yet. I'm just going to go through the process of letting x or y equal x to the m, and then take a couple of derivatives and then plug it in. So let's say y equals x to the m, y prime is equal to m x to the m minus 1, and y double prime is equal to m minus 1 x to the m minus 2. And then I'll plug all that stuff in, and I'm going to get 25 x squared m minus 1 x to the m minus 2 plus 25x m x to the m minus 1 plus y, which is x to the m, equals 0. And then I'll get all the x to the m out. So I have matching x to the m's all over the place. We have x to the mth power, and then I got 25 m minus 1 plus 25 m plus 1 equal to 0. So I'll just multiply that out and see what I can get. And 25 m squared minus 25m plus 25m, it looks like it'll cancel, plus 1 is equal to 0. So I got 25m squared plus 1 equals 0. So it looks like I'm going to have complex roots again. M is equal to, bring that over, it'll be negative. So that would be an I, and then 1 over 25 and the square root would be 1/5 I. Yes. So this thing here times this thing here is equal to x to the m. When we multiply it, and then the same thing goes with these two. So they all have x to the m there. Okay. So I have my solution m, which is a purely they call it purely imaginary solution because there's no real part, there's no alpha. And according to the formula, if we had an alpha plus beta I business, then your solution would look like x to the alpha times cosine beta ln x. But we don't have an alpha. Alpha is equal to 0, so it's just going to be the sine and cosine. I think there was a plus and minus here. So our solution should be y is equal to y1 is equal to cosine of 1/5 ln x, and y2 is equal to sine 1/5 ln x. And then your general solution. Okay. Straightforward. Hopefully you'll get to pick another one that's not sine and cosine again. So let's do another one. 5. Oh, that's the one we did earlier. I have a feeling one of these ones that don't have a middle term might work. Can we do number 4 maybe? All right. Number 4. This problem. We're going to go y. Yeah. Oh, yeah. Well, that's not going to work. Yeah, let's do a different one. 8. Oops. All right, let's see. So y is equal to x to the m, y prime is equal to mx to the m minus 1, y double prime is m minus 1, x to the m minus 2. We got x squared, m minus 1, x to the m minus 2, plus 3x, x to the m minus 1, minus 4, times x to the m is equal to 0. Then we got x to the m taken out, m minus 1 plus 3x minus 4 is equal to 0. So let's multiply everything out. We have a quadratic, m squared minus m. I suppose this should be 3m, right? Not x. Plus 3m minus 4 equals 0. So that's m squared plus 2m minus 4 is equal to 0. Got factor? Did I do that right? Quadratic formula. So from here we're going to say m is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. So this is a minus 2 plus or minus the square root of, what is this, 20? So that's like 2 root 5 maybe? So we can say negative 1 plus or minus square root of 5 if we cancel the 2's. Well, in any case, it doesn't look nice, but we have 2 distinct real roots, right? We have 2 real roots. So one's with a plus, one's with a minus. So you can just say, I'll just go straight to the solution. So the first solution would be negative 1 minus square root of 5. So it's just x to that power. And then the second one would be x to the other power minus 1 plus square root of 5, which are 2 different solutions. And then that's it. Yeah. Okay. Okay. Any questions? Yeah. Well, we don't look at it because we're going to say x to the power of m is equal to 0 because we're setting this equal to 0. And x is some range of numbers, and so we can't really find a value for m that would make this equal to 0. And so we can just say that there's no solutions, and we don't worry about that. Yeah.
The first one for y2, you need to be I sine 1 ln x, but then the I is absorbed into the C2.
You can think about it that way, yeah. Okay. Any other questions? All right, let's try another example, higher order example. Hopefully we can factor it. I don't know, number 15, 16, 17, 18. 19 is different. It's what? What? 15? So it's going to follow the same process. Your solutions are going to be x to the m. And then since this is a third order, we should expect um, 3 fundamental solutions. So when we solve for our characteristic equation, we should have 3 solutions. And then we would just count if there's anything that matches, or if there's anything that repeats, or if there's any complex numbers, then we just incorporate that. So let's see what happens in this problem. The other difference is that you're going to have to take 3 derivatives because you need to be able to put those 3 derivatives in, which means there's going to be an extra derivative term. So we have the same first 2 derivatives. The first derivative is xm to the m minus 1. The second derivative is m minus 1 x to the m minus 2. And then so you have a third derivative. It's going to be m minus 1, m minus 2, x to the m minus 3. You keep going through that process of taking derivatives. And so that's what you're going to do. Those are the things that you're going to plug in. So let's plug it in. We got x cubed, and then we have this big derivative that we just found. Minus 6. There's no more other derivatives, so we just go straight to this 6 x to the m business. And then if we multiply the x's, there'll always be factors of x to the m here, so we can factor that out. X to the m, and then what we have left is just things with an m in it. And then we hope that we would be able to factor this. Let's see if we can factor it. Let's multiply this out. This is FOIL it out. You get m squared times an extra m. The middle term is going to be negative 3m, and then multiply it by an extra m, and then positive 2m minus 6 is equal to 0. So hopefully we can factor this. We can ask Wolfram alpha. Or if you remember your algebra, it's just algebra. Remember, if you have 4 terms, the good thing to try to do is see if you can factor by pairs. How do you like that? It's kind of sweet, huh? Those factoring problems that you did in algebra saying, when am I ever going to use this in your differential equations class? So we got m squared plus 2, m minus 3. So it looks like we have one real solution, and then here we have a couple of complex solutions. So we got m is equal to 3, and then here m is equal to plus or minus the square root of 2i. So out of the m is equal to 3, you're going to get x to the m as your solution. And then out of this complex solution over here, we'll call this y1 maybe, and out of this complex solution, you're going to get two solutions, and that's with the sine and cosine. So y2 is going to be cosine, and then the constant is square root of 2, and then ln x, and y3 is equal to sine square root of 2 ln x. So a linear combination of all these fundamental solutions that are linearly independent is going to be your final answer. So we got a constant, x to the third, plus another constant, cosine, plus another constant, sine. That's it. So if you have more of them, you just count your solutions, and then whenever you have a pair of complex numbers, they become sine and cosine. Whenever you have a repeated root, which we still hadn't come up with in any of these examples, you would just repeat it and multiply it with an ln x, and that's it. It's all good in the hood. Yeah, instead of throwing an x in there like we did before, you just throw an ln x for the Cauchy-Euler equations. All right. Now let's do a real hard problem. I mean, a harder problem. This isn't too bad, is it? Nah. I think of those memes now where somebody's kind of drowning. And then in the bottom it says, "This is me in differential equations class." Um, all right. So for the non-homogeneous, it's going to be the same process because the first step we need to take is we need to find the homogeneous solutions to the homogeneous system, and then we have to find a particular solution. And so the particular solution we're going to use, or the way we're going to get the particular solution, our undetermined coefficients is not going to work for this anymore. The easy one. And so what we need to do is we need to do the variation of parameters. So variation of parameters is a good method because it always works. And if you can find an easier way to do it, then yeah. So the variation of parameter is the one that uses the Wronskian. So here you're stuck with having to use a Wronskian when you have a Cauchy-Euler equation. It's the same thing with an x, huh? I think there's something about non-matching things that would work out. Let's try to do problem number 20. '19 didn't have a matching Cauchy-Euler equation, which is still solvable. I just have to remind myself of how to solve for it. I can't remember right now. So let's do this one. Yeah. Yeah, I suppose you can. If it's equal to 0. Yeah, if it's homogeneous, you just multiply by x on both sides. Yeah. Oh well. We'll do this one. Unless you want to do the other one. Now, let's see. If I undo enough. No. Good luck. It's gonna be easy. Just do it. All right, let's try this one. So first we have to go through the homogeneous differential equation drill. Can I start skipping steps now? We just did 3 of them, right? So I remember that if I take a look at my A, my B, and my C, it's going to be A times M minus 1 plus B times M plus C, right? So that was the thing that was in the box, or equal to 0. And then I just plug in the values for A, B, and C. So in this case, A was equal to 2, is equal to 2, B is equal to 5, and C is equal to 1. So that's my characteristic equation. I go ahead and try to solve for this. 2m squared minus 2m plus 5m plus 1. So this is going to be 2m squared plus 3m plus 1. Is this a factor? Does that work? And the middle term is 3m, last term is 1. Yeah, works. So we got a couple of solutions. Distinct real roots. M is equal to -1 and -1/2. So my y1 is equal to x to the -1. My y2 is equal to x to the -1/2. So if this was a homogeneous differential equation, I'd be done. I just write this as a linear combination of C1 and C2. But I have this right-hand side. So we have to go through the variation of parameters. So this is step 1 in the variation of parameters, if you remember. I think we ended up with 7 steps with that thing. So variation of parameters, find your homogeneous system equation, then do the Wronskian, do the W1, W2, and then do the U1 prime, U2 prime, and then find the U and the U1 and U2. Okay, so let's do it. We got 7 minutes. So we are going to say our Wronskian is equal to, we have 1 over x, or x to the -1 power. Actually, let's keep it as x to the -1. X to the -1, x to the -2, or -1/2, sorry. The derivative, negative x to the -2, and then here it's -1/2 x to the negative 3/2. And so we'll take the determinant of that. We add the powers, so this would be -1/2 x to the -5/2, and minus, and then here we have a negative, so I'll just put a parentheses around a negative to keep it in control. What's this going to be? Same, right? -5/2 again. So we have -1/2 plus 1. So I think this is just going to be a +1/2 x to the -5/2. That's my Wronskian. Okay. So now I need to find my W1. So remember that W1 replaces the first column with 0 and your output, your g of x. Oh, crap. We have to erase it all. No, I'm just kidding. We just have to erase a little bit. Remember that before we figure out our right-hand side, what we need to do is we need to write this in normal form, so we need to divide out by x squared. So y double prime plus 5 halves, 5 over 2x, y prime plus 1 over 2x squared y is equal to, no, w should still be okay because w relies on just the y1 and y2. So x squared minus x divided by 2x squared. Should we leave it as this? Let's see if we can simplify it. It should just be 1/2 minus 1 over 2x. Say that again. It is, but we're not doing the undetermined coefficients, so it doesn't matter. And what's going to happen is that this will work itself out because of the Wronskians are going to take care of stuff. All right. So now that we got our I don't know, sometimes they call it f of x or g of x. But this is the function that's going to go in the columns, in the, in the columns. So go back to work with the W1 and W2. So W1 is going to be 0, and then this thing, 1/2 1 over 2x. And then we'll keep the same x to the negative 1/2 and negative 1/2 x to the negative 3/2. So the 0, I figured if I put 0 there, I'll remember that it becomes a negative because I always seem to forget the negative here. So the determinant is going to be 0 times, and then I have let's see, x to the negative 1/2 times 1/2 minus 1 over 2x. Sometimes it's a kind of a choice, and up to you to figure out how you want to deal with this. Because you're going to divide by the Wronskian, and so instead of multiplying it out, you might want to keep it separate, because when you multiply by the Wronskian, you might, see things that would cancel easier. And I usually like to do this in parallel, like W1 and W2 on the same side. But let's go through the process of figuring out W1 and then U1 prime and then U1. So U1 prime is going to be W1 divided by W, and so that's a negative x to the negative 1/2 times 1/2 minus 1 over 2x divided by W, which is 1/2 x to the minus 5/2. So let's see if we can find ways to simplify this. I think there's a 1/2 on the numerator and a 1/2 in the denominator that we can cancel. You see that? We can factor out a 1/2 in the numerator and cancel that with a 1/2. And then we have a x to the negative 1/2 in the numerator, and we have x to the 5/2. So it looks like it's x to the negative 1/2 minus negative 5/2. So that becomes positive, and then we have 5/2 minus 1/2 is 2. I think it's 2. So after canceling all that, we just have x squared times 1 minus 1 over x. And so that negative x squared plus x. Is that right? So that's u1 prime, and then you're going to find out what u is equal to by just integrating this, which is an easy integral because it's a polynomial. Negative, how do you integrate again? You add 1 to the power. So x cubed over 3 plus x squared over 2. Okay? And then part of what you're going to get is u1 times y1. So this is negative x cubed over 3 plus x squared over 2 times x to the negative 1. That's y1. And then you can just work this out. Negative x squared over 3 plus x over 2. So that's one part of your particular solution, and then you would go through the W2 and then put it all together to get your particular solution, and then you add the linear combination of y1 and y2. All right, it's all broken up into pieces. You just need to put it together, and don't make any mistakes in the middle. So I'll provide the solutions for this online. You guys can take a look at the notes.